Hello, everyone, and thank you for joining us today. My name is JC Hernandez, and I'm a tech transfer analyst at NASA Johnson Space Center. I'll be your host for this NASA Technology Transfer Program webinar on the technology Upper Robotic Exoskeleton. Our presenter today is Christopher Beck. Christopher Beck is the lead of the Wearable Robotics Laboratory within JSC's HumanWorks and has experience managing and contributing to multiple development projects related to wearable robotic devices, countermeasure systems, and physical human machine interfaces. He has a graduate degree in biomedical engineering and has been developing wearable robotic systems for over a decade. He helped develop several subsystems of the upper body robotic exoskeleton, soft upper extremity, uh, actuated garment, including the control system, the actuation load path design, and the soft physical human machine interface. Other project management experience includes the successful development of a portable knee dynamometer for use in space and in the medical domain, a medical offload solution for the upper extremities of space-suited participants in JSC's Argo system, a proprioception trainer prototype for exploration missions, and adaptations to NASA's RoboGlove for industrial applications. Following the presentation on the technology, I'll be giving a short presentation on how NASA licenses technology to outside organizations. But before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box in the lower right corner of your screen, and we will answer them during the Q&A session at the end. At this point, I'm going to turn it over to you, Chris.
Okay, thank you. Thank you for the nice introduction. And I'm happy to be here to talk about some of the technology that I've been a part in developing. So that's exciting to me to kind of get the word out outside of NASA as much as we can and see if there's potential collaboration opportunities in the future. So thank you for the opportunity. I am going to hopefully share my slides correctly. Okay, so let's see. So there we go. So I was a system engineer on the development portion of this project a few years back under Roger Rovkamp's management of the project, and obviously several other team members that all made it work. So just a little bit of background about the program that enabled this development. DARPA, which is basically the Department of Defense's research arm, if you're not familiar, they had in the kind of the mid 2010s, they had this Warrior Web program that they were basically looking for technologies, looking for industry and academia and government to develop technologies that they could apply to the warfighter in the field to increase efficiency, reduce metabolic load, mitigate risk of injury, all that kind of thing. They were also interested, apparently, because we were funded with this program, for some sort of rehabilitation of the warfighter after an injury or after they were in combat. So our focus that we proposed and were able to get funded, co-funded by them and develop our system, was on our upper body robotic exoskeleton. And this was primarily to rehabilitate warfighters who had experienced a traumatic brain injury, or TBI, out in the field. TBI presents itself with usually a cognitive impairment as well as a motor impairment. And it's really due to, we were focusing on the motor impairment aspect of it. And all of the musculature is intact, so it's not like it's much different than some sort of musculoskeletal injury or a limb amputation, something like that. It's just that in the brain, the neuromuscular pathway is disturbed. So the therapist's job is to kind of reteach that neuromuscular pathway. Our UBRE, as we've created this acronym here, was to become a soft, portable, upper extremity wearable robotic system to aid in this rehabilitation and to provide assistance for activities of daily living that the people with traumatic brain injury were no longer able to perform by themselves. For this DARPA Warrior Web program, other notable participants are shown there. So we're with some very exclusive company. So a little bit more about TBI. About 5.3 million Americans are affected by it each year. You can think of TBI as basically a concussion that's really bad. A lot worse than just a temporary concussion, but there's actual permanent damage, not just an acute issue. Impacts have led to unemployment of 60% of the affected individuals, usually on the younger side. You can kind of guess that the people who are younger are often engaging in activities that might present a opportunity for traumatic brain injury more often, whether it's sports or military applications or car accidents, things like that. We've got some other statistics here. I won't go through all of them, but a lot of people who experience the traumatic brain injuries really are just looking forward to getting back into the workforce and doing the activities of daily living that most people just take for granted around their house. So given all these statistics, we said it was reasonable to assume that improving the upper limb function for someone who had TBI would result in improved independence for that person, which of course is great for the person. It saves our healthcare system lots of dollars, and it's good all around. Current rehabilitation research indicates that task-specific and intensive practice could significantly improve this motor recovery and that neuroplasticity that I was talking about. Basically, the ability for the brain to relearn how to control specific motions, specific muscles to do specific things. So that task-specific verbiage there is referring to actually doing the thing, doing the exercise that you would do in real life, not just sitting there and doing arm curls or wrist bends or some sort of exercise like that. And intensive practice is do it a lot, as much as you can. Wearable robotic devices not only offer this movement assistance for the patient, but they also have the potential advantages of being portable so that they can be used in the home or outside. And soft exosuits have a lot of positive aspects that have been shown to increase the range of motion in adduction, elbow flexion extension, and other upper extremity degrees of freedom following stroke. And I went a little bit into the cost analysis, but comparable costs are suggested between this robotic therapy, traditional care, and intensive therapy. So there's a good bet that this is something that can gain traction in the rehab domain. So our objective mainly is to rehabilitate motor function of upper extremities in people living with TBI through this development of a soft wearable robotic exoskeleton garment. It was designed to actively control the shoulder and the elbow and position both positioning the limb in specific orientations as well as commanding the limb through the desired motions. Some technical objectives for this development was, which proved important, were distributing the load from the device around the joints so that we didn't have point loads that would really be uncomfortable or even painful. Employ safety systems with NASA heritage. Feature coordinated control so we can do some of those task-specific exercises. We utilized custom embedded firmware and software and had an enhanced user interface. We ended up developing a force controllable tendon-based actuator that was independently patented throughout this development. And we also utilize tightly packaged electronics for increased portability. That throughout the development phase of this project, we kept shrinking them down and got them a lot more tightly packaged. So as far as funding, this was co-funded by NASA and DARPA, like I said, and our team was primarily NASA. We had an academic partner with Rice University, so they provided some help with some of our research and test beds and looking into some of the controls aspects of things, as well as I'll mention in a few minutes, recruiting some actual TBI test subjects and helping get through that flow of testing them and acquiring data that we could publish. And Oceaneering is one of our NASA's contractors here in Houston, and I was at Oceaneering at the time, and we have a couple other people from that contractor working on this project. So our skill set had a strong development history of wearable robotic technologies and the physical human-machine interface, safety electronics, actuation, and control. And we also have experience accelerating TRL advancement, where we are taking going from TRL1, which is essentially you just have an idea for something, and advancing it through prototyping and design, and then collaboration with others to move it up to where it's ready to really be manufactured. If someone comes in and helps us with the design for manufacturing, the cost, servability, value engineering, that aspect of things. So we have experience with this workflow with other projects. So technically speaking, focus was to improve the functional range of motion in TBI patients. We really targeted 3 typical movements that kind of define a big percentage of the activities of daily living. One is putting your hand to your ear, putting your hand over your chest, and then reaching to a work surface. If we are able to do all of these things, you can do over 80% of the activities of daily living that a person would need to do. So in order to enable those motions, we provided we set out to provide the following range of motions for our device, which was a shoulder flexion extension range of motion between -10 and 80 degrees. That's like the bowling motion. Shoulder abduction, adduction, which is kind of like the wing flap motion of up to 80 degrees. And then elbow flexion extension, which is almost the full range of flexion extension of the elbow. And we were able to meet these self-imposed requirements with the development of the device. Let's see, a lot of this might be repetitive. Let's see, the body-machine interface was a very significant portion of this and was quite a challenge, we found out very early on. Maintaining comfort with the device throughout the range of motion is important. If it's not comfortable, no one will want to wear it. We wanted to make the device to be easily donned and doffed, which is extremely important and extremely challenging for a disabled population. We found out through our first iteration of this, we just had a sleeve, and we brought it for a traumatic brain injury patient to test out, and the person couldn't even get it on due to their disability. So we learned quickly that we'll have to go back to the drawing board and even come up with a better way to don and doff the system for this population. Let's see. We need to provide points of attachment for the tendons. I'll get more into the design here in a moment. It has to be controllable, and of course, we want to minimize the mass of the device. Always, but especially if we're dealing with a disabled population, you don't want to make it even more difficult for them to do what they're trying to do, especially distal mass. And when I say distal mass, I mean if you have a lot of mass out, on your limb that you have to throw around, that is not good to have. So we tried to minimize that, and of course, housing all the components with our body machine interface. I won't spend too much time on this, but we went through several iterations, full working prototypes to get to where we are today. I guess that was unit C.2. That was our final iteration. So we have a carbon fiber structure that was integrated into it. We chose this for its blend of stiffness and flexibility. It was really interesting that we could get really stiff behavior in one axis, but then really flexible behavior in another axis. And I can point that out with pictures as we go on here. Got our donning and doffing good. We continued to develop our software and control system algorithm that was continually being updated as things changed, and we're just improving it. Let's see. So an overview of our final iteration. Let's see. Letter A up there is just kind of the pretty artistic photograph of the front view. We only addressed the right arm, basically due to funding. We surmised that if we are able to do one limb, we could also do the other limb, and there's no reason to demonstrate right now. And maximize our dollars basically. And on the letter B, it shows the backpack of the device, which the whole device weighs less than 9 kilograms. So it basically feels like you're wearing a backpack that's full of books. So it's you can feel it there, but it's not overly cumbersome or heavy. It also can be used with a wheelchair or seated, so the weight is not on. You don't have to support the weight of it if you are not able. Let's see, the TAUs, or the TAUs we call them, or the tendon actuation units. Those are essentially the motors are housed in there, as well as everything that's necessary for the sensing and actuation of one specific degree of freedom, or robotic degree of freedom, I should say. So in order to control the shoulder, we have 4 TAUs. So that means we have 4 lines that, I don't know if people could see my cursor, but these synthetic tendons that are actually crossing over the person's shoulder here. That is the only thing that is actually controlling the shoulder or crossing over the joint, which makes it allows a very natural feel, rather than compared to like a big rigid exoskeleton, which might have a lot of heavy metal components there and might really limit the way that your shoulder can move. This does not take away any of that natural shoulder motion. So we have 4 of these to control the shoulder and 2 of them to control the elbow. I'll go back here. A little bit more of the physical human machine interface. The way that this dons is it actually is put on over the head, similar to football shoulder pads. And it can stretch out basically front and back with this carbon fiber yoke here. So this can bend to allow easy donning. And then once it's on, it fits snug against the chest and the back. And then these Velcro abdomen flaps come around, and you can cinch it down however tight is comfortable. And it's really a snug, comfortable, breathable fit. We have a soft goods team that we work with pretty closely, and they went through several iterations to work on breathability and comfort, and providing rigid components only when they were necessary, and that kind of thing. So this is kind of our optimized version here. So try not to repeat myself here, but primarily made of soft materials with only rigid components, only when we had to put them in a necessary place to provide some structure and rigidity, especially for the controllability of the limb. We have demonstrated using the device with batteries, as well as plugged into the wall. So it is portable if you use the battery option. It manipulates the upper extremity for the 3 degrees of freedom I mentioned, 2 with the shoulder and 1 with the elbow. And the wearable jacket we went over. the actuation, the power distribution, the electronics are all on that backpack. So that minimizes the distal mass. You don't have to put all that stuff out here like you would with a traditional rigid exoskeleton. A lot more of that mass would be out there and it would be cumbersome. Let's see, less than 9 kilograms. We have synthetic tendons that are routed through that gold conduit. Let's see. And basically the way that everything is actuated is there's it's almost like a marionette, like an automated marionette. So each of those tendons that are crossing the shoulder and the elbow, they are pulled in such a way using our control algorithm that the computer that resides in the backpack can easily say, I want the arm to go to a certain position real time, and we're doing this at 1,000 times per second. Each one of those independent actuators are pulled exactly where the synthetic tendon is exactly the correct length to position the shoulder and elbow properly. So that allows a kind of this symphony of marionette control that you can get with this distributed control in the backpack. Let's see, maximum joint torque values for this design is between 25 and 50 Newton meters, depending on the person's anthropometry as well as which joint you're talking about. Every degree of freedom, human degree of freedom, can be moved at greater than 30 degrees per second. So it wasn't designed to be super speedy, but importantly, all the components are scalable if smaller or larger joint torques or slower or faster joint speeds are desired for a particular application. When we were doing the design for this device, we penalized a large volume because you don't want to be walking around with this big, Mega Man, Iron Man type of thing out in public, or it's cumbersome and you get some weird looks. And we wanted to penalize that to maintain its wearability and its portability. Distal weight, like I mentioned, was minimized. Structured components were integrated only when necessary, and we did it so that it did not impede the wearer's movement. Talked about the actuators and the TOWs, and everything in the TOW. There's a motor with an encoder, so you know how long that cable is at every given time. There's a pulley, a tension sensor, so you know what the tension is on that pulley. There's a redundant force sensor just for safety, and then the conduit and the cable itself. I won't go into too much detail about the electrical and software, but everything's in the backpack, and we have some FPGAs acting as our main processing units, and we use EtherCAT for our communication for the electrical engineering nerds out there. More for sensing and control. Now, this is the important parts, the control modes for either the person who's being rehabilitated or basically providing the ability to mimic their activities of daily living if they are not able to do it. We have 2 shoulder joint IMU sensors. One is on the clavicle and one is on the upper arm. That basically provides the data for what the orientation of the shoulder is, and that feedback goes back into the control system so that it can respond and tell the motors how much to pull on each tendon to put the arm in the desired orientation. And the several modes I'm talking about are the active assist mode, where basically the device just the operator can tell the device to go to a certain trajectory, or I shouldn't say trajectory, just orientation of their shoulder and elbow, and the device will just put the person there. So it doesn't really require the person to do anything. In passive mode, that's kind of just the opposite. where the device just provides minimal torque and kind of gets out of the way of the person. So if a person is progressing in their rehabilitation and they're able to do more and more and more, we would use more of this passive mode where the person is really doing a lot of the control. And only in the fourth mode, I'll skip over the third mode, but in the assist as needed mode, the device will only kind of kick in and help only when it's needed to help. So if the person is, for example, following a trajectory on a screen during a therapy session, and they're doing a great job and they're nailing the trajectory perfectly, the device will really just kind of get out of their way and not help at all. When they need a little bit of assistance and they're not following that trajectory very well, then the device kind of kicks in and helps them complete the trajectory. So from a neuroplasticity standpoint and encouraging that neuroplasticity in the brain, it's best to have the person do the full motion themselves to retrain that neuromuscular pathway. However, it's still very good to have the device control them if they are not able to. Let's see, we have an intuitive user interface displays real-time commanded versus actual position so that the person can see how well they're doing and respond accordingly. We use a cascaded control scheme to ensure individual joint tracking from the high-level controller that resides in the backpack. Yeah, this is kind of getting in the details here. We have a minimum tendon force of 1 foot-pound. That was, or I believe 1 pound. That was levied on each tendon just so the tendons don't go slack, and then it's difficult to control. And we've got, of course, safety measures in here. The way that we physically designed it to not allow hyperextension. We have constant 1 kilohertz safety loop running that is checking against limits for all of the sensors coming in, and if there is a exceedance of past a limit, then the device safes itself. I'll move on to we ran 1 case study for it ended up being two people who had a traumatic brain injury and were living with that. I won't go into much of the detail here. If you're interested, you can go to that bottom link here and see the publication that we have as far as the who these people were and their demographics. That's more here. But the subjects participated in up to 4 sessions for some engineering evaluation, as well as donning the device, practicing how to don and doff, seeing how long it takes, learning from that, trying to iterate to make it better, taking data for comfort, et cetera. So a lot of subjective data gathering. But then we also actually put the device to work. And with our physical therapist that was on the team, we developed some protocols for them to test and to see if this device could provide any reasonable benefit that we could actually tease out of only just having 2 subjects. So there's nothing that's going to be statistically significant here with only 2 subjects, but it was really proving the concept that this device really could be used for traumatic brain injured patients and provide some benefit. So here's a picture of each of those subjects. The person on the left was just sitting on a bench, and the person on the right was in a wheelchair. So we demonstrated, that was one of our things that we demonstrated, is that this could be used in a wheelchair or just sitting. We also demonstrated it standing, but that picture is not shown here. So some of our results, I won't go into much time on this, but basically we showed that stabilizing the shoulder, let me back up a second. For traumatic brain injured patients, a lot of times they have difficulty isolating joint movements from one another. For example, if you tell a person to flex their elbow or bend and extend their elbow, they might try to do that, but at the same time put a lot of shoulder into it because the location of their brain injury is such that they do not know they no longer know how to inhibit that shoulder motion. So they couple all of that motion together. It is the physical therapist's job traditionally to try to decouple those motions. So the person really, when they want to bend their elbow, they bend their elbow and they don't have to move the rest of their body with it, right? So what we were able to show with this device is that if we stabilize the shoulder, so use our device to basically lock that shoulder in place and then allow the person to follow a trajectory just with their elbow motion, they were able to perform this isolated elbow rehabilitation with no loss in the range of motion. And what that does, so because they're able to do it with no loss in their range of motion and their shoulder is isolated, that really helps decouple those two motions in the brain. So that is one thing that our physical therapist on our team was going after is making sure we had a device, that we were developing a device that could help out with doing that. So this data showed that was true. One more plot here, and this is the last one I'll bore you with, but this was just one of the TBI subjects in active assist mode, where basically the device is moving the person for them, and they're just kind of along for the ride. And it really shows the desired versus the actual, and shows that they're pretty close. So what this in effect shows is that the device is able to control a certain trajectory with a TBI subject inside the device. So what we were able to demonstrate in the lab with our healthy people that were on the engineering team is that we could program different activities of daily living, such as reaching for a cup and picking it up and putting it to your mouth, or reaching for a light switch and turning it on or off, opening a refrigerator door, things like that. We were actually able to record the person doing that motion while they were in passive mode with the device, where the device just lets you do what you want. So we recorded that data, and then we could instantly play it back in active mode, and then the device would replicate that same exact motion for the person. So what that demonstrates is that we could come up with some canned motions for any particular individual, or record them on the fly as needed, and that person could select that motion and the device could move that for them if that person had such a disability that they weren't able to do any of that for themselves. So just a summary of this technology and what it's capable of. The main takeaway is that it can actuate the upper limb to a desired real-time orientation for therapy, assistance, and or augmentation in either disabled or healthy populations. One thing I didn't talk about is all of the applications for the healthy populations. So mainly touched on the medical applications, but there's also industrial and construction applications as well as military applications. So I talked just briefly a moment ago about how the device was able to, for example, reach for a cup, pick it up, put it to your mouth. That type of assistance could be used for any industrial application where like a repetitive motion is done, like on a factory floor during assembly or what have you. Augmentation to allow if you had to pick up something that weighs 50 pounds, if you put some augmentation in there, maybe now it's only effectively 25 pounds or 10 pounds or 0 pounds. Depending on how you would scale that up. It is also, like I said, scalable for larger torques and velocities. These components, all you have to do is make them bigger, and all of the underlying engineering holds true. You just have to find a place to make sure that all of that joint load is properly distributed across the chest and the back, which we have done with our novel suit. It's also translatable to other human joints, so it's not just the shoulder and the elbow. We've also investigated the knees and the hips, especially with spacesuit integration. We're looking into that. It has an integrated safety system, like I mentioned, the tendon-based actuator, and custom physical human-machine interface garment optimized for comfort and control. That does distribute the load around those joints to reduce forces and increase comfort. And then again, all the tightly packaged electronics allow portability and wearability, so you're not confined to the clinic if you're going to your therapy session. So that is all I have, and I thank you everyone for joining and for their attention.